Picture yourself standing at the edge of a cliff in the Sierra Nevada mountains, 1878. Below you, a ravine drops nearly 2,000 feet. The air smells like pine pitch and sawdust. Behind you sits a freshly cut sugar pine log, 16 feet in diameter and weighing close to 150 tons. There's no helicopter coming. No crane exists that could lift this thing. The nearest railroad is 40 miles away, and even if you could get there, the terrain between here and there would swallow a wagon whole. Your boss tells you this log needs to reach the sawmill in the valley by sundown, and you're going to move it down that cliff, using nothing but gravity, timber, and a system so elegant in its brutality that it would make modern engineers question everything they know about material science. This is how America built itself. Not with machines that came later, but with the bodies and ingenuity of men who looked at impossible geography and said, "We're going down anyway." The forests that 19th century America desperately needed sat in the worst possible locations. The Pacific Northwest coast ranges rose like walls between the ocean and the interior valleys. The Sierra Nevada mountains climb to 14,000 feet, their western slopes covered with the largest trees on Earth. The Great Lakes region sprawled across terrain so boggy and roadless that wagons sank to their axles within miles of the tree line, and every major city, every railroad, every expanding farm needed wood. Staggering, almost incomprehensible quantities of wood. San Francisco burned to the ground 6 times between 1849 and 1851. Each time it rebuilt larger than before. The city consumed lumber at a rate that stripped entire hillsides bare within months of cutting. By 1860, the easy timber around the bay was gone. The remaining forests sat 50 miles inland and 5,000 feet up. Getting that wood to market meant crossing terrain that horses couldn't climb and wagons couldn't navigate. Chicago's Great Fire of 1871 destroyed over 17,000 structures in a single night. The rebuilding effort required lumber shipments that taxed every mill in the Great Lakes region. Lumber prices tripled overnight. Men who had ignored distant stands of timber suddenly found those trees worth fortunes. And they looked at mountains they'd previously considered inaccessible and saw dollar signs instead of obstacles. The transcontinental railroads needed 200 million wooden ties by 1890. Each tie required a tree. Trees that increasingly grew only in places where no train could reach. The Pacific Railroad needed timber for bridges, trestles, station buildings, fuel depots, and the endless fuel that steam locomotives consumed. Every mile of track westward required lumber that came from somewhere, moved by someone through terrain that shouldn't have allowed it. The problem wasn't just distance. Distance could be solved with time and enough animals. The problem was vertical terrain, so severe that traditional transport methods simply didn't work. A bull team could drag logs across flat ground reliably. 8 oxen working in tandem could move a 30-ton log at walking pace across reasonable terrain. Teams of 16 oxen could handle even larger loads. The animals were strong, patient, and relatively inexpensive to maintain. They ate grass that grew everywhere. They bred reliably. They died slowly enough that their replacement costs could be planned for. But put those same oxen on a 20-degree slope and they couldn't hold the weight. The log would start sliding, pulling against the chains, gaining speed, crushing anything in its path. Oxen couldn't work going downhill on any significant grade. Their legs couldn't brace against the force. Their hooves couldn't grip the soil. And the best timber sat at the top of mountains that made 20 degrees look gentle. Horses were faster, but weaker. A good horse team might move a 10-ton log on flat ground. They were more nimble than oxen, better at turning corners and navigating obstacles. But on slopes, they were worse than useless. A sliding log would catch up to the team and kill both horses and drivers before anyone could react. The horse's natural instinct was to run from danger, which only accelerated the disaster. The conventional wisdom of Eastern logging simply did not apply out west. The white pines of New England grew on gentle hills near rivers that flowed year-round. You could fell a tree, roll it to the water, and float it to the mill with minimal engineering. The entire industry had evolved around that basic pattern. Generations of loggers had perfected techniques that assumed cooperative terrain. Nothing about Western timber matched those assumptions. The Douglas firs of Oregon grew on cliffsides above rivers that raged during spring runoff and dried to trickles in summer. The sugar pines of California grew at elevations where snow accumulated 20 feet deep, making winter work impossible and summer work a desperate race against the returning cold. The coastal redwoods stood in groves so dense and the trees so massive that falling one often destroyed 3 others around it. The sequoias were in a category of their own. A mature sequoia could weigh 2,000 tons. No team of any animals could budge it. No road could support it. No wagon could carry it. The very characteristics that made these trees valuable, their immense size and perfect grain, made them nearly impossible to move. The men who figured out solutions came from everywhere. Failed gold miners who knew how to read terrain because their lives had depended on finding gold deposits in hostile landscapes. Norwegian immigrants who'd seen timber operations in Scandinavian mountains and understood that steep didn't mean impossible. Scots-Irish farmers who understood water and gravity from generations of irrigation work in difficult terrain. Chinese laborers who'd built the railroads through the Sierra Nevada and knew exactly what could be done with blasting powder, determination, and disregard for human life. They invented an entirely new engineering discipline. Call it gravity logistics. The science of making heavy things go where you want them to go, using nothing but the planet's own pull and whatever materials came to hand. The earliest solutions were crude beyond belief. In the 1850s, timber operators on the Mendocino coast simply rolled logs off cliffs into the ocean. The surf would batter the logs against rocks, breaking many of them into worthless splinters, but enough survived intact to make the practice profitable. Men with boats would collect the floating logs and tow them to mills down the coast. The waste was astronomical. Surveys from the period estimate that 60% of the timber rolled into the ocean was destroyed before it could be recovered. 6 out of every 10 trees cut, gone, smashed against rocks or swept out to sea or waterlogged beyond use. But the wood was essentially free for the taking. The demand was insatiable, and there were always more trees up the cliff. This couldn't last. As the easy coastal timber disappeared and operations moved inland, the cliff-rolling approach became impossible. The timber now sat miles from any water deep enough to absorb the impact. Some stands grew above valleys that dropped 2,000 feet to rock floors. Rolling logs into those valleys didn't transport them. It destroyed them. A new method was needed. The log chute emerged from this necessity. The concept was simple enough that a child could understand it. Build a channel. Make it smooth, grease it up, point it downhill. Let gravity do the work. The execution was anything but simple. James Wickersham, working the forests near Puget Sound in 1871, built what many consider the first properly engineered chute in the Pacific Northwest. Wickersham had been a carpenter before the timber industry found him, and he understood wood at the molecular level. He knew that friction generated heat. He knew that heat plus dry wood plus pine pitch equaled fire. And he knew that a burning chute full of moving logs was about as close to hell on earth as you could manufacture on purpose. His solution involved water, not flooding the chute, which would slow the logs too much and waterlog the wood. Just a steady trickle along the bottom, enough to keep the wood cool, enough to wash away the accumulated pitch and sawdust that could ignite. The water would evaporate almost instantly as friction heated the wood, creating a steam layer that actually reduced resistance while preventing combustion. The V-chute design that Wickersham perfected became the industry standard for 50 years. 2 heavy planks, typically 4 inches thick and 12 inches wide, arranged at a 60-degree angle. The geometry was precise, too wide an angle, and logs would bounce from side to side, potentially jumping the rails and crashing into the forest. Too narrow and only small diameter timber would fit. Building these chutes required skills that have largely disappeared from the world. The chute builders worked without levels, without surveying equipment, without the benefit of topographical maps that didn't exist yet. They read terrain by walking it over and over, studying how water flowed during rain, estimating grades by the feel of their legs burning on the climb. A good chute builder could look at a hillside and tell you within 5% what the average grade was across a mile of terrain. He could identify the spots where logs would accelerate dangerously, and the spots where they'd slow too much and need a steeper section. He could see, in his mind, show the entire pathway a log would travel before the first timber was cut. Building the chute itself was backbreaking and lethal work. The crews worked from the bottom up, constructing each section on supports driven into the hillside. On steep terrain, the supports might be 20 or 30 feet tall, essentially building scaffolding before building the chute itself. Each support had to be perfectly positioned to maintain the calculated grade. An error of even a few inches could create a bump that would send logs airborne at killing speed. The supports were typically made from the same timber they'd eventually be moving. Douglas fir for strength, redwood for rot resistance. The irony was constant and unspoken. They were building infrastructure to move trees using other trees, and sacrificing some of the forest to extract the rest of the forest. Michael O'Brien joined the Pacific Lumber Company's chute construction crew in April of 1881. He was 26 years old, recently arrived from County Cork, drawn to California by letters from a cousin who described wages that seemed impossibly high to men earning Irish labor rates. O'Brien had been a farmhand in Ireland. He'd never built anything more complex than a stone wall. He was assigned to the Devil's Slide section, a stretch of chute that dropped 800 vertical feet in less than a quarter mile. The terrain was so steep that workers tied themselves to trees while working, like mountaineers on a rock face. The name wasn't poetry or exaggeration. Men died there with regularity. The chute had earned its name through accumulated bodies. On the 11th day of O'Brien's employment, a staging plank gave way beneath him. The plank had been reused from an earlier project, and rot had weakened the fibers in ways that weren't visible on the surface. O'Brien fell 90 feet before hitting the rocks below. His crewmates couldn't reach him until the following day. The terrain was too unstable for safe descent, and company policy prohibited rescue attempts in darkness. O'Brien was almost certainly dead from the initial impact, but nobody could confirm that until they recovered his body. The recovery itself took 3 days and nearly killed 2 more men. The company recorded his death as accidental fall and charged his family $12 for the transport of his remains to San Francisco for burial. The chutes killed builders during construction. They killed operators during use. They killed bystanders who stood too close. But the logs kept moving because the alternative was bankruptcy. Once built, a log chute required constant attention and careful operation. The friction between moving logs and stationary wood generated tremendous heat, even with water flowing. On dry summer days, chute operators would station men every few hundred yards to watch for smoke rising from the channel. At the first sign of heating, they'd dump extra water from buckets kept full for exactly this purpose. Fires could spread from the chute to the surrounding forest within minutes if not caught. The grease used to reduce friction was itself a science that operators debated endlessly. Early operations used animal fat, rendered from whatever was available locally. Beef tallow worked well but was expensive. Lard was cheaper but less effective in hot weather. Fish oil was abundant on the coast, but smelled so bad that workers vomited while applying it, and the logs themselves arrived at the mill reeking. Eventually, the industry settled on a mixture of crude oil and rendering fat that balanced cost, effectiveness, and the ability of workers to tolerate the smell. The crude oil came from early California oil fields, making the timber industry one of the first large-scale consumers of petroleum products in the American West. Loading logs into the chute was an art form that took years to master. The loader, called a top dog in most operations, had to position each log precisely so it would enter the channel straight. A log that entered at even a slight angle would bind against the sides, potentially jamming the entire system or launching over the rails into whatever stood below. The top dog worked with a peavey, a heavy pole with a metal spike and hook, rolling logs that weighed tons with nothing but leverage and practice skill. Once the log entered the chute, physics took over completely. Acceleration was immediate and dramatic. A log that entered at walking speed would be doing 30 miles per hour within seconds, 40 by the time it reached the first curve, 50 or 60 by the time it hit the bottom section. The howl of wood against wood echoed off canyon walls for miles. The ground trembled like a small earthquake. Birds exploded from trees half a mile away at the sound of each log starting its descent. The bottom of the chute was either the most dangerous or the safest place on the entire operation, depending entirely on perspective. The logs arrived at terrifying speed, but they arrived predictably. The splash pond workers knew exactly where each log would land, exactly how much spray it would throw up, exactly how long they had before the next one came screaming down the mountain. Patrick Sullivan worked the Scotia Splash Pond for 16 years, from 1889 until he finally couldn't walk well enough to do the job anymore. He developed a technique of standing perfectly still until the last possible moment, then stepping aside with a motion so economical it looked almost lazy. The log would crash past him, spraying water and bark and God knows what else, and Sullivan would already be reaching with his pike pole to guide it toward the raft. Sullivan estimated he personally witnessed 11 men die on the job during his tenure. Crushed between logs that collided unexpectedly, knocked into the water and held under by the churning mass, struck by fragments when logs shattered on impact with rocks hidden just below the surface. He lost 3 fingers of his own to log strikes, mangled when a pike pole kicked back unexpectedly. His pelvis was crushed in 1891, giving him the lurching walk that became his trademark around town. When a journalist from the Sacramento Bee asked why he kept working the pond, Sullivan's answer was brutally practical. His other option was the mines or the canneries. At least on the splash pond, you could see death coming. You could time it, predict it, dance around it if you were good enough. In a mine, the roof fell without warning. In a cannery, the machines didn't care whether you were paying attention. The chute system worked brilliantly for terrain that dropped consistently toward a destination. But timber doesn't grow in convenient locations. Sometimes the forests sat behind ridges, requiring the logs to go up before they could go down. Sometimes they sat across valleys that no continuous chute could span. Sometimes the terrain was so complex that no single method could handle all of it. Water provided the answer to terrain that chutes couldn't conquer. Not just water for cooling friction, but water as a transportation medium in its own right. The logging flume was essentially an artificial river, built from scratch through wilderness that had never seen human construction of any kind. The principles were ancient. Romans had built aqueducts that carried water across miles of terrain. Like mining operations had long-used sluices to move material downhill. Canal builders in the East had shown that water could be made to flow wherever engineers wanted it to go. But nobody had attempted water channels at the scale the timber industry required. The Kings River Flume in California, completed in 1890, ran 54 miles through the Sierra Nevada mountains. It dropped over 4,000 feet in total elevation. It crossed canyons on trestles that stood 100 feet high and stretched hundreds of feet long. It wrapped around cliff faces where the drop below was measured in hundreds of feet, not tens. It diverted water from multiple creeks into a single channel that ran constantly, day and night, for months at a time. Building this flume was a construction project that rivaled the Transcontinental Railroad in difficulty, if not in fame. Crews worked from both ends toward the middle, surveying routes through terrain that had never been mapped. They built access roads just to reach the construction sites. They established camps that became temporary towns, complete with cookhouses and bunkhouses and the inevitable saloons and brothels that followed working men into the wilderness. The main line needed a constant flow of at least 600 cubic feet per minute to maintain transportation speed. During drought years, supplementary streams had to be tapped from miles away. During flood years, elaborate spillway systems had to prevent the channel from overtopping its banks and washing out the supports below. The flume boxes were built from carefully selected lumber, typically sugar pine or redwood depending on availability. Each box was 12 feet long, typically 4 feet wide at the top, narrowing to about 18 inches at the bottom in the characteristic V shape. This geometry centered the floating logs, preventing them from jamming against the sides where friction would slow them down. Connecting the boxes required precision that seems almost impossible given the tools available. The joints had to be watertight enough to prevent significant leakage while still allowing for thermal expansion. Wood swells when wet and contracts when dry. A joint that fit perfectly in morning mist might gap by afternoon and leak water into the valley below. A joint that was too tight would buckle and crack when the wood expanded. The flume walkers, men who patrolled the channel looking for problems, covered their entire section every single day regardless of weather. Walking 54 miles of flume on catwalks barely 18 inches wide, with nothing between them and the ground but air and trestle work that creaked in the wind. They carried tools for minor repairs and signal flags to halt operations if major work was needed. Thomas Chen walked the Kings River flume for 8 years. He was one of thousands of Chinese workers who moved from railroad construction to timber after the transcontinental lines were completed. He estimated he covered over 100,000 miles during his tenure, the equivalent of walking around the entire Earth 4 times while balancing on a plank. Chen developed an almost supernatural ear for problems. He claimed he could hear a loose board from 50 yards away, could detect a crack in a trestle support by the pitch of the wind through the framework, could tell when a joint was about to fail by a subtle change in how water sounded flowing over it. His supervisors thought he was exaggerating until they started checking his predictions. He was never wrong. Chen died in 1898 when a section of catwalk collapsed beneath him during a routine inspection. The timber had rotted from the inside, showing no external signs of weakness. He fell 60 feet into a dry ravine that the flume crossed on an elevated trestle. His replacement started the following week. The section was repaired in 3 days. The splash dam represented the most violent method of timber transport ever devised, and paradoxically, sometimes the only one that worked. In regions where the terrain was too flat for chutes but too rough for flumes, where rivers existed but didn't flow reliably year-round, the splash dam turned seasonal streams into weapons of mass lumber transportation. The concept was devastatingly simple. Build a dam across a stream. Let water and logs accumulate behind it through an entire cutting season. When enough material had gathered, blow the dam open with dynamite and let physics do the rest. The pressure behind the dam would do in minutes what months of steady flow couldn't accomplish. The Menominee River in Wisconsin saw some of the largest splash dam operations in history. A single dam on that river might hold 50 million board feet of timber gathered over an entire cutting season. The water behind it would rise 30, 40, 50 feet. The pressure at the base of the dam was tremendous, measured in thousands of tons of force pressing against wooden planks and earthen fills. When the dynamite exploded, the effect was a man-made tsunami. A wall of water and logs would rush downstream at speeds approaching 20 miles per hour. Everything in its path was destroyed or swept along. The wave from a major splash could travel 30 miles before dissipating completely, taking 4 or 5 days to fully pass any given point. People living along the river learned to watch for warning signals and get their livestock and valuables to high ground. River drivers followed these artificial floods in boats, on foot, and occasionally on the logs themselves. Their job was to keep the timber moving, to break up jams before they became disasters, to rescue logs that escaped the main channel before they were lost to sandbars or backwaters. The log jam was the nightmare that haunted every river drive. When logs piled against an obstacle, the pressure behind them built with mathematical inevitability. Thousands of logs, millions of pounds of force, all seeking the path of least resistance. Somewhere in that snarling mass of timber was a key log, the one holding everything else in place like the keystone of an arch. Finding the key log required experience that no classroom could teach. The river drivers would walk out onto the jam itself, feeling the vibrations through their boot soles, listening to the groans and creaks of stressed wood, probing with their pike poles while standing on a surface that could collapse at any moment. The jam was alive in a way that non-loggers couldn't understand. It breathed, it shifted, it was constantly searching for release. Joseph Montferrand became legendary throughout Ontario for his ability to read jams. He worked the rivers for 40 years, claiming to have broken over 400 major jams without ever being caught in a release. When asked his secret, Montferrand said the logs talked to him. He could hear which one was holding the rest. He just had to listen carefully. On September 14, 1891, a jam on the French River released while Montferrand was standing on it. Witnesses said he was reaching for what he thought was the key log when the jam let go without any warning. The logs beneath him suddenly separated and began moving. Montferrand went into the churning mass of timber and water and never came up. His body was found 3 miles downstream 2 days later, wedged between 2 massive logs that had somehow protected his corpse from further damage. He was 63 years old. He'd been talking about retiring after that season. The incline railway solved a different problem entirely. Sometimes logs needed to go up before they could go down. Sometimes the mill sat on a ridge while the timber sat in a valley below. Sometimes terrain required approaches that seemed to violate the basic laws of physics. The principle of the incline was elegant counterweighting. A heavy car loaded with logs would descend on one track. Its weight, transmitted through a cable running over a drum at the top, would pull an empty car up the parallel track. The 2 cars balanced each other, with the difference in weight providing the motive force. Load one car heavier than the other, and gravity did the work. The balance had to be precise within a few hundred pounds. Too much weight on the descending car, and the system would accelerate beyond control, potentially snapping cables and killing everyone in the vicinity. Too little weight, and the ascending car wouldn't have enough pull to climb the grade. The operators worked without scales, judging weight by eye and decades of experience. George Stevens ran the incline at the Columbia River Lumber Company for 22 years without a single serious accident. He never weighed a load in his life. He would walk around the descending car, tap on each log with a wrench handle, and tell his crew exactly how many board feet to add or remove. After his retirement in 1907, the company installed proper scales for the first time. They discovered Stevens had been accurate to within 3% on every single load he ever judged. When asked how he did it, Stevens said the logs told him how heavy they were if you listened. Every man who worked with him tried to learn his method. None of them could do it. The physics of these operations would make any modern engineer pause. Consider the forces involved in a typical chute run. A log weighing 50 tons, accelerating at roughly 2 feet per second squared on a 30-degree grade. By the time it traveled 1,000 feet, it would be moving at over 40 miles per hour. The kinetic energy at impact was measured in megajoules, enough to shatter concrete if concrete had existed in those quantities. The friction coefficients that the chute builders calculated by instinct are documented in engineering textbooks today. Wood on greased wood has a friction coefficient of roughly 0.1 to 0.15, depending on the grease used. That means only 10 to 15% of the gravitational force is absorbed by friction. The rest becomes acceleration. The builders knew none of this math, but they understood the relationships perfectly through trial and error and dead men. The structural loads on the chute supports were equally remarkable. A moving log doesn't just press down, it creates lateral forces as it rounds curves, centrifugal acceleration that tries to throw it off the track. The chute curves had to be banked like a racetrack, higher on the outside to counteract this force. Getting the banking wrong meant logs leaving the chute at the worst possible locations. Temperature changes complicated everything. A chute built perfectly on a cool morning might warp by afternoon as the sun heated different sections unevenly. Wood expands when heated. The side of the chute facing the sun would grow slightly longer than the shaded side, creating subtle curves that weren't part of the original design. Experienced operators learned to account for this, building their chutes with slight compensating curves that would straighten out as the sun rose. Water flow rates in the flumes required similar precision. Too little water and logs would drag on the bottom, too much, and they'd ride too high, potentially jumping the rails on curves. The optimal depth was approximately 2/3 the diameter of the log being floated, maintaining that depth across 50 miles of channel, through sections that crossed creeks and sections that lost water to evaporation, and required constant adjustment and monitoring. The donkey engines that powered high-lead operations were marvels of industrial violence. These steam-powered winches could generate forces measured in hundreds of tons. The cables they wound were made from steel wire rope, a relatively new technology in the 1880s. Each cable strand had to be tested before use. A cable failure under tension didn't just break, it whipped. A snapping cable could cut a man in half at distances of 50 feet or more. The high lead system represented the ultimate evolution of gravity-based timber transport. Instead of moving logs along surfaces, whether greased wood or flowing water, high lead operations lifted them completely off the ground and flew them through the air to collection points. The system required a spar tree, a tall, strong specimen left standing after the surrounding forest was cleared. Riggers would climb this tree, sometimes over 200 feet tall, using nothing but spiked boots strapped to their feet and a rope belt around the trunk. At the top, they would cut away the crown and install the pulleys and guy wires that transformed a living tree into an anchor point for an aerial transportation system. The climbing itself was a spectacle of controlled terror that drew spectators from miles around. Ascending a tree trunk 12 feet in diameter with nothing but spikes and grip strength between you and certain death. The climbers moved upward like human spiders, wrapping their belts around the trunk, digging in their spikes, ascending foot by foot through bark that crumbled and branches that tried to knock them loose. And Daniel Mercer was 23 years old when he climbed the tree that would kill him. The Weyerhaeuser operation near Tacoma needed a new spar after their previous one had been damaged by lightning, and Mercer was considered the best climber on the crew. He reached the top in just under 4 hours, a remarkable time for a tree of that size. Topping the tree was the final and most dangerous act. Mercer had to saw through the trunk while attached to it, removing the upper section so the rigging could be installed. As the cut deepened, the top section began to lean. Mercer had done this dozens of times before. He knew exactly when to make the final strokes, exactly when to duck against the trunk, exactly when the tree would kick backward as the weight above separated. Something went wrong that nobody fully understood. Eyewitnesses said the top section twisted as it fell, somehow catching Mercer's climbing rope and ripping him from his position against the trunk. He fell 170 feet. The impact sound carried half a mile. The tree was named the Widowmaker after his death. Nobody on that crew considered changing it. The statistics from this era are almost numbing in their scale. Washington State reported in 1912 that logging had a fatality rate of 3.24 deaths per 1,000 workers per year. If you worked on a crew of 50 men for 6 years, statistically speaking, someone you knew and worked beside would almost certainly die on the job. The deaths weren't random. They clustered around certain operations, certain methods, certain weather conditions. Spring was worst, when melting snow made everything slippery and unpredictable. Monday mornings were deadliest, when workers were still shaking off weekend drinking. New hires died at 3 times the rate of experienced workers. The first month on any job was the most dangerous month you'd ever work. And yet the logs kept moving. 200 billion board feet from the Pacific Northwest between 1870 and 1920. Another 100 billion from the Great Lakes. More from the South, from what remained in New England, from every corner of a country that was building itself from raw timber. The numbers are difficult to comprehend in human terms. 200 billion board feet is enough lumber to build a solid wooden wall 1 foot thick and 100 feet tall, stretching from New York to Los Angeles, and back again, twice. Every piece of that wood was cut by hand, moved by gravity, guided by men who earned between $2 and $4 per day and consider themselves lucky to have the work. The productivity of these operations increased every decade as methods improved. The Kings River Flume moved 50 million board feet in its first year of operation. By its 5th year, improved techniques had pushed that to over 100 million. The difference was experience. Men learned which woods floated best. They learned how to load logs so they wouldn't jam. They learned the rhythm of the water and the behavior of wood until the knowledge became instinct. The accident rates decreased too, though they never approached anything resembling safety by modern standards. The fatality rate dropped from roughly 5 deaths per 1,000 workers in the 1870s to just over 3 per 1,000 by 1910. That improvement came from bitter experience. Every death taught something. Every close call refined a technique. The men who survived longest were the ones who paid attention to the men who died. The economic impact of these timber operations shaped entire states. Washington's economy was essentially synonymous with logging until well into the 20th century. Oregon's population centers developed around mills. California's growth was literally built from timber transported through the chutes and flumes of the Sierra Nevada. This lumber built the railroads that connected the coasts. It built the cities that rose from empty prairies and muddy coastlines. It built the ships that crossed oceans and the bridges that crossed rivers, and the factories that would eventually make the machines that replaced the men who built them. Every piece of that wood passed through systems like the ones we've explored today. Every board in your grandmother's farmhouse, every beam in those old brick factory buildings, every piece of virgin lumber and antique furniture, all of it rode gravity down mountainsides, floated through artificial rivers, flew through the air on cables, and was handled by men who knew they might die doing the work. The techniques didn't disappear entirely. They evolved and spread. High lead systems became modern construction cranes. Flume engineering influenced aqueduct design throughout the West. The incline railways directly inspired the funicular system still operating in San Francisco and cities around the world. The men who survived timber work carried their knowledge into construction, into dam building, into every industry that needed to move heavy things through difficult terrain. But the old growth forests are gone now. The massive trees that made these operations possible don't exist anymore outside a handful of protected reserves. The last significant log chute closed in 1934. The last commercial splash dam was blown in 1929. The last traditional high-lead operation, using hand-rigged spar trees, shut down in the 1960s. What remains are artifacts scattered through the wilderness. Rusted spikes driven into ancient stumps that served as dead men anchors. Collapsed trestle work half buried in vegetation. Depressions in the ground where flume boxes rotted into the soil over decades. The forest is reclaiming what was taken, slowly erasing the evidence of what happened here. And the men are remembered only in accident reports and company ledgers and brief newspaper death notices. Michael O'Brien, Thomas Chen, Joseph Montferrand, Daniel Mercer, thousands more whose names were never recorded at all. They appear in history as statistics, as labor costs, as the inevitable price of progress that nobody wanted to pay, but everybody accepted. They built America down the side of a mountain. They moved the immovable. They solved problems that seemed impossible using nothing but physics, timber, and their own bodies. The wood remembers what we've forgotten. Run your fingers along the grain of old-growth lumber sometime. That grain recorded everything. The mountain it came from, the chute it screamed down, the water it floated through, the hands that guided it, and the men who died getting it there. That's the story we forget when we look at old buildings and old furniture and old photographs of frontier towns. Someone moved every piece of that wood. Someone risked everything to transport it from where it grew to where it was needed. Someone built this country with nothing but gravity and blood. If you made it to the end, you're not here for surface level content. You want the real history, the version that doesn't look away from the cost. Subscribe, because next week we're exploring another piece of engineering that built this country and killed the men who made it possible. That video is on screen now.